Welcome to The Explainer. Today, we're diving headfirst into the absolutely staggering scale of our global waste crisis and the cutting-edge tech that's stepping up to solve it. We're currently facing an unprecedented bottleneck of electronic and plastic waste that's literally testing the limits of our planetary boundaries. But the good news? We're also going to look at how artificial intelligence and unified policies are offering us a very real way out.
Let's kick things off with a number that honestly sets the stage for everything we're going to discuss today. 448 million tons. By 2015, global plastic production skyrocketed to that massive figure. To really put that into perspective, back in 1950, we were only producing 2.3 million tons. And if we stay on our current trajectory, that 448 million is projected to double by 2050.
Why is that number so terrifying? Well, it's all about how we consume. Think about this. Over 40% of plastic is used literally just once before it gets tossed away. Couple that with the fact that electronic waste, or e-waste, is rising 5 times faster than documented recycling, and you can see why our landfills simply cannot keep up. Rapid urbanization, combined with our constant desire for the newest tech, has completely overwhelmed our global waste infrastructure.
So, here's our roadmap for today. We'll cover 1. The global waste crisis. 2. Hidden health and environmental impacts. 3. Global legislation and EPR. 4. India's waste management realities. 5. AI-powered waste classification. And finally, 6. Achieving a circular economy.
Right. Let's jump straight into Section 1, the global waste crisis.
The sheer scale of this leakage is wild to think about. Every single year, a massive 8 million tons of plastic pour into our oceans from coastal nations alone. To picture that, imagine lining up 5 full garbage bags of plastic on every single foot of coastline around the entire world. And because of the chemical additives used to make these plastics durable, they can take over 400 years to decompose. Meanwhile, international agreements like the Basel Convention, which were designed to stop illegal waste trade, are struggling. There's this huge loophole where e-waste is exported under the guise of reuse, which leads to massive dumping in developing nations where the equipment is practically useless.
Moving on to Section 2. Hidden health and environmental impacts. Because, this stuff doesn't just magically disappear. Sunlight, wind, and waves break it all down into microplastics, tiny particles less than 1/5 of an inch across, and they are literally everywhere. We found them at the icy peak of Mount Everest, and all the way down in the dark depths of the Mariana Trench. Globally, nearly 2,100 species are being severely impacted by this pollution, usually through swallowing it or getting tangled up in it.
And perhaps unsurprisingly, it's climbing right up the food chain to us. The health implications here are intense. We are now detecting microplastics in human blood, lungs, and even placentas. Beyond just the physical particles, toxic additives like phthalates and BPA act as endocrine disruptors, leaching straight into our soil and water. When plastics are burned out in the open, they release toxic dioxins and furans into the air. And when e-waste is dismantled improperly, hazardous components like mercury and cadmium directly poison local air and water supplies, which is just devastating for human health.
Next up, Section 3, Global Legislation and EPR.
So, how are governments handling this? Well, central to a lot of legislative efforts is a concept called EPR, or Extended Producer Responsibility. In plain English, this is a policy approach designed to shift the financial and physical burden of waste management back onto the companies that actually manufacture and distribute the products. Basically, if you make it, you are responsible for what happens to it at the end of its life.
But looking at the data globally, the application of these laws varies wildly. Take Europe, for example. They benefit from a unified regulation system known as the WEEE Directive, which mandates free collection points and strict treatment standards right across the continent. The US, on the other hand, takes a highly fragmented approach. There's no sweeping federal law. Instead, just 25 states have their own e-waste recycling laws. And these range dramatically. You've got California, which funds recycling through consumer fees, all the way to Connecticut, which assigns strict producer recycling quotas based on market share.
Let's zoom in on a specific case study in Section 4, India's waste management realities.
India is dealing with an overwhelming 55 million metric tons of municipal waste every single year. But what's incredibly unique about their situation is their reliance on a robust, informal sector. These grassroots networks actually manage to recycle about 70% of plastics and 27% of paper. It is a massive, commendable effort, but even with that, severe structural hurdles mean that coastal and urban pollution remains a critical threat to both their environment and economy.
While it's great that 60% of collected plastic waste gets recycled there, we can't ignore the other side of the coin,
A massive 40% remains entirely unaccounted for. That mismanaged waste often ends up choking urban drainage systems, like we've seen during the devastating Mumbai floods, or washing out to severely pollute India's extensive coastline. So the really crucial question becomes, with millions of tons of waste generated globally and huge gaps in accountability, how on earth do we efficiently sort it all to make sure it actually gets recycled?
Which brings us to Section 5, AI-powered waste classification.
If we're ever going to shift away from these overflowing landfills, we need to realize a circular economy. And making that a reality requires highly accurate, automated sorting of waste on a massive, industrial scale. Manual sorting simply can't keep up with the volume or the complexity of modern waste anymore. This challenge has sparked an incredible breakthrough in artificial intelligence. Recently, researchers at the University of Hull decided to tackle this head-on. They put together a massive data set of over 25,000 waste images. Their goal was to train AI models to accurately tell the difference between organic waste, stuff like food scraps or coffee beans, and recyclable waste, like aluminum cans and paper. They even augmented these images, resizing them and converting them to grayscale with edge detection to really force the AI to look at structural patterns.
And the winning deep learning architecture for this task was something called DenseNet 121. Now, this isn't just your standard computer program, it's a deep convolutional neural network. It passes visual data through a series of complex, dense blocks and transition layers. Because each layer receives inputs from all the previous ones, the network can pick up on incredibly subtle structural patterns that traditional computers, and honestly even humans, would completely miss.
The results were nothing short of staggering. When put to the test, this DenseNet 121 model hit a 91% accuracy rate and a near-perfect 0.98 ROC-AUC score. It absolutely demolished traditional machine learning methods. For context, things like random forest algorithms were sitting way back at 71%. By integrating this level of AI into smart city infrastructure, we can automate waste sorting with an unprecedented level of precision.
Finally, let's look at the big picture in Section 6, achieving a circular economy.
Bringing AI into our sorting facilities drastically empowers long-term recycling strategies by guaranteeing pure, uncontaminated material streams. But listen, technology alone isn't a magic wand. We desperately need short-term behavioral shifts too. Think widespread awareness campaigns to drop single-use plastics, alongside long-term policies that fund R&D for reusable packaging. We have to treat the reduce and reuse parts of the equation just as aggressively as recycle. And the data totally backs this up. Research indicates that if we implement comprehensive life cycle policies, meaning we regulate plastic from its initial production, through its use, and all the way to its disposal, we could reduce plastic leakage into the environment by an astonishing 96% by the year 2040. Compare that to a narrow focus just on waste management at the end of the line, which only gives us a 55% reduction. The takeaway is clear. We have to stop the waste at the source.
So why does all of this matter so deeply? Because fixing this crisis directly tackles at least 6 of the United Nations Sustainable Development Goals. We're talking about everything from good health and clean water to sustainable cities and life below water. Managing our e-waste and plastics isn't just some abstract environmental issue anymore. It is literally a human survival and economic imperative. I want to leave you with a really powerful quote from the research we reviewed today. We weren't aware of the implications for plastic ending up in our environment until it was already there. Now we have a situation where we have to come from behind to catch up. As we look ahead to massive international efforts like the UN Treaty on Plastic Pollution, the technology is catching up, but it needs our help. So ask yourself, how can you shift your own consumption habits today to support the circular economy of tomorrow? Thanks for joining me on this explainer, and keep questioning how we can build a better system.